Dr. S. Nagan. He is an associate professor in civil engineering at Tyagarajar College of Engineering, Madurai. He pursued his undergraduate and postgraduate studies from Tyagarajar College of Engineering and completed his PhD at the Madurai Kamarajar University. He has more than 20 years of teaching and research experience. He has worked in many prestigious institutions including PSNA, College of Engineering and Technology, Dindigul. He has published more than 25 research papers and 5 books under his name. Apart from all this, he is a life member at the International Society for Environmental Protection and also at the Indian Society for Technical Education. To add to all of this, he is won the Best Staff Advisor at the ISTE Students Chapter.
Welcome to UGC lecture series for Bachelor of Architecture. In this lecture, we will continue to see the analysis of deflection of beams. Earlier, we have analyzed deflection of cantilever beams by double integration method and by moment area method. In the moment area method, we have been seeing an additional example that we will continue first and then we will proceed to calculating deflection of simply supported beams using Macaulay's method. So, that is the topic to be covered. Now, we have been seeing an example of a cantilever beam subjected to 2 point loads. So, the area of first portion, so we have divided the bending moment diagram into a triangle and rectangle like this. So, we had the bending moment diagram like this, which comprises 3 portions, one triangle, another rectangle and triangle. So, first area we have computed and then the next CG distance we need to find for area 1. So, CG distance for area 1 will be from this end, it will be 2/3 the length, which is 1, 2/3 of 1, this is 0.67 meter, and then area 2 we have already computed is the area of a rectangle, and CG distance will be this distance, the distance from here, and the CG of the rectangle will lie exactly at the center. So, that will be again 1/2. So, this is 1 meter and this is 1/2. So, x 2 will be 1 plus 1/2 and A 3 is again area of a triangle. So, half into BH and then x 3 CG distance will be, we already have 1 meter up to this, then 1 plus we have the triangle like this. So, from this end the CG will be lying at a distance of 2/3 of the length. So, 1 plus 2/3 into 1, that is 1.67 meters. So, once we have in hand the area and the CG distances, then it will be easier to compute the moment of area of the bending moment diagram about the point B. So, moment of area of the bending moment diagram divided by EI will give the deflection at point B, and this is C and this is A. So, we can compute deflection at B by computing the moment of area of the bending moment diagram up to point B divided by EI, and that will give us 0.002615 meters. Since we already have the value of EI, we get deflection as 2.61 millimeters. Now, if we want the slope up to C or slope at C, say we have 2 point loads A, B and C, we have computed the deflection at C or B, we have computed deflection at B, that is y B we have obtained. Now, if I want y C and theta C, slope at C as well deflection at C, say if I want slope at C, I need to find the area of the bending moment diagram up to C. So, we have the bending moment diagram like this, a triangle, a rectangle and another triangle. So, we comprises 3 portions. So, if we compute the area up to C, so if we compute this area of the portion 2 and 3 alone, then that will give the slope at C. So, slope at C is area of the bending moment diagram up to the point C. So, that is again we need to remember from the definition of moment of area or area, if we want slope of at any point, we need to find the area of bending moment diagram up to that point alone. Similarly, if we want deflection at any point, find moment of area of the bending moment diagram up to that point. So, now we want at C. So, calculate area up to C, similarly moment of area up to C. So, A 2 plus A 3 divided by E I will give you the slope at C. Similarly, the deflection at C will be moment of area up to C divided by E I, and that will result in as 1.225 mm. So, this is how we should compute the slope and deflection by moment area method. Next, we will see the concept of arriving slope and deflection in case of simply supported beams. And for simply supported beams, the easiest method is to go by Macaulay's method. So, in this example, we will see how Macaulay's method is which is a refined double integration method, which is applied to a simply supported beam. So, we will take a simply supported beam with central point load, and we know that E I d squared y by dx squared equal to minus m x x. So, we need to derive or arrive the value of m x x for portion A C and for portion B C before proceeding to the substitution of the bending equation. So, if we consider portion A C, say we have the simply supported beam subjected to central point load. So, this is A and this is B and this is C. So, before proceeding to bending moment equation, we need to have the value of the reactions, and for problems like this, a symmetrically loaded beams, the reaction will be simply symmetry. So, it will be equal. So, R A will be equal to R B and it will be equal to W by 2. So, if I consider or if we consider portion A C, a section in portion A C x x and x distance from the left end, then bending moment at x x will be equal to W by 2 into x. We have a load of W by 2 to the left side of x, and that will produce a clockwise moment. So, left clockwise being positive, we have the sign convention left clockwise, left anticlockwise, right clockwise and right anticlockwise, plus minus minus plus. This is the bending moment sign convention. So, left we have W by 2, distance is x, W by 2 into x, it produces clockwise moment, left clockwise being positive. The m x x in portion A C is W by 2 into x. Now, if we move over to portion C B, say same example, say we have A, B, C, consider our section in portion B C, consider section in portion B C, and this distance will be x. And we will also need the distance between this load W and your section. So, that will be that distance will be this, since this is L by 2, this distance will be x minus L by 2. Therefore, the bending moment at x x will be equal to W by 2 into x. So, left we have reaction W by 2 multiplied by distance x, which produces clockwise moment. So, plus W by 2 into x, and then we have this applied load W that will produce an anti-clockwise moment with respect to x, and its value will be W into x minus L by 2. So, now we are ready with the equations of bending moment for portion A C and for portion C B. Now, we can substitute in the general bending equation, that is E I d squared y by dx squared equal to minus m x x. So, if we substitute in this equation E I d squared by dx squared equal to minus m x x, we have minus m x x, we have values for two portions, and if we notice the equations will be W by 2 x for portion A C and W by 2 x minus W into x minus L by 2 for portion C B, and if we notice there is a common term in both the portions, the common term will be W by 2 into x. So, while writing the equation m x x in the right side of the bending equation, we can use this pattern, that is we have E I d squared by dx squared equal to minus, first write the m x x value for portion A C, that which is W by 2 into x, then put a dotted line and write the term which is extra in portion C B or extra for portion C B, leaving the common term, because W by 2 x is already been written, we can leave that term, put a dotted line and write the extra term available in the second equation or the second equation for portion C b, which is minus w into x minus L by 2. And if we operate the minus sign on both, we will get minus w by 2 into x with a dotted line plus w into x minus L by 2. So, this is our first equation. Now, we are going to proceed by the method of double integration. It is a refined method of double integration. We will have the common terms before the partition line and then we proceed. That is the change in the refined method of double integration. Now, integrating equation 1, we get E I dy by dx equal to minus w by 2 x squared by 2 plus C 1 constant of integration with the dotted line plus w into the, here we need to remember that we have term x minus L by 2. We have the term x minus L by 2 after the dotted line, that should be treated as a single term, that should be treated as a single term x. So, we should not separate and integrate, we should not separate x and minus L by 2 and then integrate. We should have the term x minus L by 2 as a single term, say imagine it as capital X. So, if we integrate capital X, we will get x squared by 2. So, we have x minus L by 2, which should be integrated. After integration, it becomes x minus L by 2 whole squared by 2. So, this is equation 2. So, we should remember this point at this juncture, that is after the partition line we will be having terms, those terms will be should be considered as a single term, those terms within bracket should be considered as a single term for integration, should not be separated and integrated, that is more important. And then if we integrate 2 with respect to x, you will have E I y equal to minus w by 2 x cube by 6 plus C 1 x plus C 2, then dotted line plus w into, already we have the term x minus L by 2 whole squared by 2, that should be treated as a single term, x minus L by 2 should be treated as a single term, therefore, it will be x cube by 3, already we have 2, therefore, x minus L by 2 whole cube by 6. So, now we have the equations for slope and deflection with some constants of integration. So, the constants of integration can be found by substituting the boundary conditions. So, we very well know boundary conditions. So, in case of cantilever beam, we let us recall what are the boundary conditions. So, this is the way how the cantilever beam will deflect. So, at x equal to L, y equal to 0 and at x equal to L, dy by dx equal to 0. These are the boundary conditions for a cantilever beam, whereas a simply supported beam will deflect in this fashion. So, it will be deflecting like this. So, it will have some slope at A, it will have some slope at B and somewhere the slope is 0 and the deflection will be maximum at the center in case of symmetrically loaded beams and it will be somewhere where slope is 0. Now, the boundary conditions will be at x equal to 0, deflection is 0, that is very well seen from the way the beam deflects. Similarly, at x equal to L, y equal to 0. These are the two boundary conditions which are need to be substituted in the equations to get the constants of integration. So, when x equal to 0, deflection is 0. Similarly, at when x equal to L, deflection is 0. We can use these two boundary conditions in equation 3. Earlier, in case of cantilever beams, we substituted one slope boundary condition and one deflection boundary condition, but here we are substituting two deflection boundary conditions. So, using boundary condition 1 in equation 3. So, while employing the boundary condition in equation 3, care should be taken that the boundary condition is applied up to the dotted line, because x equal to 0 lies in the region AC. So, we have the simply supported beam A, B, C, we have the simply supported beam A, B, C and we are use the boundary condition when x equal to 0, y equal to 0, when x equal to L, y equal to 0. So, x equal to 0, y equal to 0 lies in the region AC, lies in the region AC. Therefore, while substituting this boundary condition, we need to substitute up to the dotted line, thereby we get C 2 equal to 0. And then we can substitute the boundary condition 2 in equation 3 for the entire equation, because the boundary condition 2 is x equal to L, y equal to 0. So, x equal to L means the entire equation can be made use of for substituting the boundary condition. So, this implies 0 equal to minus w by 2 L cube by 6 plus C 1 L plus w into L minus L by 2 by 6 whole cube. So, we are putting x equal to L. So, simplifying we get the value of C 1 as w L squared by 16, C 2 is 0 using the boundary conditions which we substituted earlier. Then we can obtain the general equation for slope as E I dy by dx equal to minus w x squared by 4 plus w L squared by 16 with the dotted line plus w into x minus L by 2 whole squared by 2. This is equation A. Equation A is the general equation for slope. So, we have the simply supported beam, AB and load is applied at point C. So, we need to know up to dotted line when we should use the equation and when we should use the entire equation. So, if we require slope value at any point in portion AC, let it be A or let it be C or anywhere in between, if you want the slope value, then the slope equation has to be used up to the dotted line. Say for example, if I want slope at A, I need to substitute x equal to 0 in this equation A up to the dotted line, and then we will get the value of slope. Similarly, if I want slope at C, for that also I can use say x equal to L by 2, because C lies at midpoint. So, x equal to L by 2 in this equation A up to the dotted line, I will get the slope at C. When I want slope at any point beyond C, then we can use the entire equation removing the dotted line. This is to be noted and this is to be remembered for obtaining the values of slope at any required point. So, the entire equation need to be used for portion for any point in portion CB, and equation up to dotted line need to be used for any point in portion AC. Similar way, we can obtain the general equation for deflection as E I y equal to minus w x cube by 12 plus w L squared by 16 into x dotted line plus w into x minus L by 2 whole cube by 6. So, this equation is general equation for deflection. So, if we are interested in obtaining deflection for any point in portion AC, we can use the general equation for deflection up to dotted line, and if we have any point in portion CB and if you want deflection at that point, we can use the entire equation removing the dotted line and substituting appropriate value for x. The advantage of Macaulay's method. So, you may see what is the advantage of Macaulay's method. Say if we do not go by the method of partitioning like this, then we will involve equations for two portions separately. So, if we simply adopt the double integration method, which we are familiar already, then each portion will involve two constants of integration, and altogether 4 constants of integration have to be found by substituting the available boundary conditions. Whereas, here by Macaulay's method the constants reduced to 2 and we can easily substitute 2 boundary conditions to get the 2 constants of integration. That is the advantage of Macaulay's method. And moreover, if we involve more number of loads, and definitely we will involve number of portions. So, any portion can be partitioned like this, and then leaving the common term we can write the extra term in the other portion and then proceed in the manner which we discussed now. Now, I want slope at the supports. So, I want slope at support A. So, slope at support A, we have the simply supported beam AB subjected to central point load W C. I want slope at A. So, as we discussed, I need to put x equal, or we need to put x equal to 0 in the slope equation up to the dotted line. So, if we put 0, then we will get slope at A, which is represented as E I theta A, which is equal to W L squared by 16, or theta A will be equal to W L squared by 16 E I. This will give you the slope at A, and if we are given numerical example, if we have the values of the load, the span Young's modulus and moment of inertia, you will get theta in radians by substituting the values. Similarly, if I want slope at B, I need to put x equal to L in the entire equation, because x equal to L lies in region C B. So, we need to put the entire equation, thereby we will be getting slope at B, and slope at B we get as minus W L squared by 16 E I. We know that the deflection will be maximum where slope is 0. So, here a simply supported beam, it deflects in this manner. It will have some slope at support A, it will have some slope at support B, and somewhere the slope will be 0. So, if we are able to find where the slope is 0, then at that point deflection will be maximum. So, deflection will be maximum where slope is 0. So, how to find the point where slope is 0? So, let us assume that it lies in portion AC, the maximum point lies in portion AC. So, we can equate the slope equation up to dotted line to 0. So, equating that we will get minus W x squared by 4 plus W L squared by 16 equal to 0. Therein we will get x equal to L by 2. So, that indicates that at x equal to L by 2, slope will be 0 and deflection will be maximum. So, if you substitute the value of x equal to L by 2 in the deflection equation up to the dotted line, you will get the value of maximum deflection. So, maximum deflection will occur at x equal to L by 2 where slope is 0. So, substituting this value we get maximum deflection as W L cube by 48 E I. So, this is a standard case. So, a simply supported beam with central point load is a standard case, and slope at supports theta A will be equal to theta B equal to plus or minus W L squared by 16 E I, and deflection will be maximum at the center. So, deflection Y C will be equal to W L cube by 48 E I. So, these are the standard values for standard loading case. Similarly, at this case we can also will remember what is the deflection in case of point load in case of cantilever beam. So, the slope at B will be equal to W L squared by 2 E I, and deflection at B Y B will be equal to W L cube by 3 E I. So, these are standard loading case wherein we need to remember the values of slope and deflection, or we can easily arrive the values of slope and deflection. Now, we will see another example of a simply supported beam of span 2.8 meters carrying a point load 60 kilonewton at 1 meters from the left end, and the remaining distance B C will be 1.8 meters. So, this is an example that change in this difference between the earlier example and this is earlier we had central point load, and now we have a non-central load or an eccentric load. So, in this case how we are finding the or going to find the slope and deflection at different points. So, before proceeding we need to find the reaction at supports. In the earlier case, if the problem being symmetrical, we found the load is reaction is W by 2 on either side. In case if we have non-central load, the reactions can be found using W B by L and W A by L. Say we have a simply supported beam and we have load W acting at distance A and this is distance B, then this reaction will be W B by L and this reaction at B W A by L, that is reaction at A will be W B by L and reaction at B will be W A by L. So, we can use this formula to calculate the reaction at the supports. Even if we do not know the formula, then we can find the reactions using the static equations of equilibrium like sigma V equal to 0 and sigma m equal to 0. So, initially use sigma V equal to 0 to get the reactions R A and R B, and then use sigma m equal to 0 and take moments about any of the supports, we can get the reactions. So, finding reactions is important in case of simply supported beams as we had discussed already. So, once the reactions are known, mark the reactions and have the and apply the load. Now, we have two portions, portion AC and portion CB. So, consider section in portion AC. Consider section in portion AC at distance x. We have reaction A as 38.57 kilonewton. So, bending moment at x x will be equal to 38.57 multiplied by x, and it produces clockwise moment, left clockwise being positive. So, plus 38.57 into x. Then portion C B, we have portion C B, A, B, C. Consider section x x and let the distance be x. So, now we will be requiring the distance between the 60 kilonewton load and section x, which will be equal to x minus 1 meters, because we have x up to the section x and portion AC is 1 meter. So, x minus 1 will give the distance between the 60 kilonewton load and your section. So, now bending moment will be this reaction 38.57 multiplied by x minus 60 into x minus 1. So, we should be familiar with finding this bending moment at any section, which we have already we are conversant in the unit 1. In the unit 1 we have studied how to carefully calculate the shear force and bending moment at any section. So, that knowledge will help here in finding the bending moment at any section. Now, to obtain the slope and deflection equations, we have E I d squared y by dx squared equal to minus m x x. So, E I d squared by dx squared equal to minus 38.57 x, use a dotted line, minus 60 into x minus 1, because this 38.57 x is common for portion AC and CB. So, that we are not repeating. So, as we did in the earlier example, you write once and then differentiate by a dotted line or separate by a dotted line and write the additional term alone. In case if we have one more portion, we can leave the first two terms, or we can take the first two terms as common terms, and the extra term can be written beyond the dotted line. So, we get E I d squared by dx squared equal to minus 38.57 x plus 60 into x minus 1, that will be equation 1. Then we need to go by double integration. So, integrating 1 with respect to x, we get minus 38.57 x squared by 2 plus C 1 plus you put a dotted line plus 60 into x minus 1, that x minus 1 term should be treated as a single term. So, if we integrate capital X, we get x squared by 2. So, 60 into x minus 1 whole squared by 2. So, that will be the second equation. Then integrating equation 2 with respect to x, we get E I y equal to minus 38.57 x cube by 6 plus C 1 x plus C 2 dotted line plus 60 into x minus 1 whole cube by 6. Again we need to remember that the term after the dotted line should be treated as a single term and integrated and not separated. So, x minus 1 will be treated should be treated as a single term, and single term capital X, and capital X when integrated we get x squared by 2, and when integrated again we get x cube by 6. That is what we have followed here. So, to sum up what we have studied so far, we have started the case of simply supported beams, and we have introduced the concept of Macaulay's method. In the Macaulay's method, first generate the bending moment equation for each portion, and while writing the bending moment equation in the equation E I d squared by dx squared equal to m x x, have common terms left behind the dotted line and additional terms after the dotted line, wherein you involve only two constants of integration. Substituting the constants of the boundary conditions, the constants of integration shall be evaluated, and then the general equation for slope and deflection can be obtained, and slope and deflection at any required point can be obtained by substituting the appropriate x values. Next questions: what is the advantage of Macaulay's method? Then express slope and deflection in case of simply supported beam subjected to central point load. Then how will you obtain maximum deflection, or where will you get maximum deflection? And you may be given numerical examples, like this, that is you will be given a simply supported beam and you may be given a central point load of 60 kilonewton, say 3 meters A, B, and you will be asked to calculate theta A, theta B and y c. So, this sort of examples we can expect. Similarly, the load can also be a non-central load, as we discussed in the previous example. It will be say 10 kilonewton, 3 meters, 1 meters. So, in that case we need to calculate the slope at supports and also the maximum deflection at the points and also deflection under the load point. Thank you.